So in this experiment, we'll be talking about E by M of an electron. Here we'll be using Thomson's method. So the apparatus for this is a ruler, a magnetometer, a scale. We use an electron gun and a pair of magnets. Word of advice in this experiment, always we'll be using the interaction of unlike pair and not unlike pair. Make sure the magnets are kept as far as possible. Get the compass on the ground. Find out where is the zero deflection. Check that. Let it settle for some time. So as you can see from the top, with a good measurement, try to make sure you mark it up. Shift this. You just draw up a line. Right. Now this will act as your line of reference to place the ruler. Right. Tips for keeping the ruler, what I would follow is try to place it right on the line rather than trying to check it if it's aligned after you keep it on it, as this can provide a good line of reference. So once that is done, this one, you keep this back in such a way. It's here. You keep this back in such a way that it looks perpendicular. Like if this is the apparatus, your zero should be somewhat like this. Right. Once it's done, without disturbing that part of the equipment, place this. Eventually, it will settle down. Should be about.
It's exactly at zero. Right?
Yep.
It's exactly.
Yep.
Almost.
It's exactly. So now it is settled down. So what you do is, two more things you'll have to keep in mind. First thing is that when this line is there, it should be running straight to this. That's another thing we do. You can make minor adjustments here and there if needed, not a problem. But make sure
the line should exactly be parallel, as much as possible.
Yeah, as much as possible. And the second thing is, make sure this distance between both should be as equal as possible. Because what you're doing is when you're measuring from the center of the needle to the edge, you'll be measuring for length. And at that time, from here to here should be equal to here and here.
Basically, what you have to do is measure this distance. Wherever you keep the magnet, measure this distance. Do it however you can.
Yeah, do it however you can.
Measure it from the center.
Try to keep the unlike poles away because that is what will be used. So for the first, another thing which the professors have told is try to keep the deflection between 50 and 60 degrees. So you will be able to do it properly, and you won't have much of errors in your electron when you're placing the electron gun. So for starting, let's take 13 centimeters. So this is already 7. So 8, 9, 10, 11, 12, 13. So 76. That's 13 from here. And when you're keeping this, make sure the needle and the bar magnet should be in a straight axis.
Yeah, keep it parallel to the scale. Okay, right? I mean, what he means is, don't keep it like this or like this. Keep it exactly parallel to the scale.
Even if you're keeping it over here, it'll go wrong.
Yeah.
It'll have to be here itself.
Okay.
Similarly, it was 7, 8, 9, 10, 11, 12, 13. So it is over. See, as I've kept this, you'll see that you will observe a deflection. Observe a deflection on the magnetometer. Wait for it to settle down. Once it's settled down, you can observe it. Now it's somewhere between 50 to 60. Now take in the readings.
So while taking the readings again, make sure that the reflection is covered by the needle itself.
Now for one kind of a setup, you get two readings. One is this and this.
Yeah. For example, this is 55 and 56, right?
Yeah.
Those are the two readings.
Okay.
So this is for one configuration.
Yeah, that's for one configuration. Once you've done that, invert both. So now again, remember it's in unlike poles. Once you do that,
second configuration.
Same configuration you are taking in.
Okay, what is the next configuration?
That's done. Once that's done, inverse the magnets. Okay. Remember, in all the times when we are doing this,
it's always unlike poles.
Once you do that, again you take it. That will be a theta 5 and theta 6. Then flip it back for one last time. That will be theta 7, theta 8.
Okay.
Now for one distance, you'd have got 8
values
for theta.
For configuration, each configuration 2 values. So those 8 theta values, you'll have to plot it here.
For now, you ignore what these values are. Just seeing this much of the paper. So that is right. You get 8 sets of values. Take the mean.
So the distance you measure from the center, and the theta you measure, you have to make sure that the reflection is not seen, and you have to measure it from the center. For configuration, each configuration 2 values, so total 8 values.
Just try to keep it within 45 to 60.
Yeah, 45 to 60. So that's the corresponding distance will be what? 13 and above.
Yeah.
Right? 13 and above.
So you can see this. Even if you keep it from 30 to 60, you get in a beautiful range. So make sure you have such kind of a range. Once that is done, we go to the second part of the experiment. The magnets.
Do not disturb this. Okay. So the guideline is for this purpose itself. If it's disturbed, you can parallel to the guideline.
And then placing the electron gun. Again, when you're placing in the electron gun, the main focus is, you see the plates of separation are over here, which are connected for the electron gun. So make sure that is in parallel axis to this. Once that setup is done, we switch on. Now you can see initially you can see the voltage is 0 over here. As I told, this device connected to the electron gun. At the starting, you've just shown as a reference that when both are on very different angle, this is what you'll be able to see. There's nothing but electrons firing rapidly on the given screen. So with a little bit of toggle on intensity and the focus, you should be able to get something. You should get something of a very small dot. One more beautiful thing is you can always change the X shift. Yeah. Y shift you cannot. That is only by giving in voltage, but that will come in later. Now you can see, as you can see, this is not in 0. It is not in 0. So as far as the calibration that goes, we cannot really calibrate it back to 0. But wherever it is for you, okay, take that as your 0 line. Alright, right now I think it's at 4.4. If for some devices it might be at 0, for some devices it might be at 0.4, minus 0.4, doesn't matter. Take that as your 0 line. So at first I kept it on 13 centimeters. That would be here and here.
13 centimeters, right?
Yeah. Again, same rules. Make sure that the parallel to they're on the same axis as this, and not here and there, no turns. Okay. Once you've done that, you can see there's a sudden spike.
Yeah.
So it was earlier over here.
Yeah.
And it comes over here.
Yeah. Right. Perfect.
Right.
So he has exactly taken 13 centimeters. Okay, from the center.
Okay. So once we have set that up, you can see the deflection is changed, and now it has gone up. Alright. So what you can do is, first you measure where it is.
Yeah.
So suppose this 0.4, this 0, so that's 0.1, 0.2, 0.3, 0.4, 0.5. So it has taken a deflection of 0.5. That is going to be your Y shift.
Yeah. So where do you measure the distance from? You measure the distance from your 0.
Not
so
this 0.
Not this 0, your 0 line. So our initial 0 line was 0.4, right?
Yeah.
So from 0.4, what is the distance? That distance.
Yeah, that distance you measured. Now once you've measured that, when you note down, that'll again help you at the end formula. So once you've done that, start increasing in voltage. Now you see, when I start increasing in voltage, it starts going up. Alright, this sometimes happens. So when that happens, you can toggle it to reverse. This. Okay, so here that means it needs negative voltage to fall down. Now you see, now it is starting to come down. You can see it's trying to return back to its original position. Now I have to give enough voltage so that it comes back to its original position. Now this was my original position. So now you have to see how many volts you have supplied to that. That's it. Yeah, you can see how much voltage you have supplied. That will be taken as V, voltage. Now similarly, now you don't have to do any much calibration, because the earlier time you had to take in 8 sets because you are calibrating as to what value it would have been. Now what you would have initially noticed is when you are taking theta 1, theta 2, they would have varied by a degree or 2. So for that calibration you kept shifting. But here you don't need it. Now like that, for 4 different
distances, just take 4 readings here.
4 different distances, like that 4 different V values you get.
Yeah.
Now when we come back to the theoretical point, you remember the earlier mean which you had taken degree? Find out tan of that. And then as I told you, note down the vertical shift.
Vertical shift. So vertical shift is basically when you keep the magnets, how much it shifts. Okay, up or down.
It can be up or down. You don't have to mark it as negative or something. Just take the modulus. Vertical shift, and then voltage for what it comes down.
So after you keep the magnet, it vertically shifts. Then you increase the voltage, right? It comes back to that your 0 position. So whatever is the voltage, for it to come back to your 0 position, that you will write here.
Right. Now later we come back to the formulas. Our general formula, that is E by M, is nothing but 2 into voltage into Y shift by KB square. Let's use this formula, KB square, where K is always given on the equipment. That is nothing but separation of the 2 plates. That you cannot generally do it, so it is given on the board. That is a K, and then B square. What do you know for B? B is nothing but BH tan theta. As a formula, BH is always given to you.
Yeah.
BH is a constant that will be given to you.
So tan theta you have found out.
So now you know tan theta. Now you're going to put in the formula. BH is given. So BH into tan theta. Once you find in BH and tan theta, you can then put it in B square. K value you know. Now when I told you about Vy, that is nothing but voltage into vertical shift into 2. So 2 into vertical shift into voltage.
It's not V subscript Y, it's V into Y.
V into Y, 2 into V into Y divided by K which is given and B square which you found out. E by M value will be coming around something like this. So that's what this experiment is all.